All right, let's dive right in. Today, we are pulling back the curtain on the amazing tech that lets our phones and computers make sense of the visual world. It's called a convolutional neural network, or CNN for short. It's the brains behind pretty much all modern image recognition, and we're going to break down exactly how it works. So let's start with a really basic question. When you and I look at a picture, our brains just see things. We see a face, a car, a landscape. But what does a computer see? I mean, how does it go from a bunch of colored dots to actually knowing what it's looking at? And this happens all the time, every single day. Your phone unlocks just by seeing your face. An app suggests tagging your friends in a photo. A self-driving car spots a stop sign and, well, stops. This isn't just some clever party trick. It's a really powerful type of AI doing its thing. Okay, so the first thing you have to get your head around is this. For a computer, a picture has zero meaning. It's just data, a giant grid of numbers where every single number just represents the color and brightness of one pixel. So the whole game starts by translating what we see into the only language a machine really gets, math. And that image isn't just a flat grid. It actually has depth. You've got the height and width in pixels, sure, but then you've got 3 of these grids stacked right on top of each other. There's one layer for red, one for green, and one for blue. This big, 3-dimensional block of numbers, that's the raw clay our AI is going to mold. So, how in the world do we get from that big block of numbers to recognizing, say, a cat? For the longest time, this was a massive, massive challenge in computer science. But then came the breakthrough, the convolutional neural network. Here's the really cool part. Instead of a programmer trying to write code to tell the computer what a corner or an edge looks like in pixel numbers, which is practically impossible, a CNN learns all of that by itself. It starts with the raw pixels, and then layer by layer, it builds up a more and more complex idea of what's in the picture. Okay, so let's pop the hood and peek inside this feature factory. To make this easy, just think of our CNN as a feature detective. Its only job is to find clues in all that pixel data and then piece them together to solve the ultimate mystery. What is this a picture of? And our detective? It has a very specific 3-step method that it just repeats over and over again. First, it finds clues. Second, it decides which clues actually matter. And third, it simplifies everything to focus on the best leads. Let's walk through each one. First up, convolution. Picture a tiny little magnifying glass called a filter. This filter is trained to spot just one simple thing, like a perfect vertical line. It slides over every single part of the image, and whenever it finds a match, it lights up and makes a note on a new map. We do this with dozens of different filters, one for horizontal lines, one for curves, one for a certain shade of blue, and we end up with a whole stack of these clue maps. Okay, next, our detective has to sort the good clues from the junk. That's where a step called ReLU comes in. It's a super simple but crazy powerful move. It looks at all the signals from the filters and basically asks, is this important? If a feature is strong, ReLU lets it pass through. If it's weak or just noise, it gets tossed out, turned to 0. This step is absolutely crucial because it helps the network focus only on the signals that matter. And finally, our detective needs to simplify the case. This is called pooling. The network takes each of those clue maps and shrinks it way down. How? By looking at small patches and keeping only the absolute strongest signal from each patch. It's like a detective summarizing pages of notes down to a single bullet point. It makes the whole process faster and helps the network see the forest for the trees. Now, having this process is one thing, but actually training a model to be smart and reliable, well, that's a whole other ballgame. There are some classic traps that engineers have to work really hard to avoid. And the number one enemy is something called overfitting. This is what happens when the model doesn't really learn what a dog is. Instead, it just memorizes the exact pictures of dogs it was shown. So the second you show it a new dog, a dog it's never seen before, it has no idea what to do. So yeah, the difference between memorizing and truly learning is everything. Think about it. A student who just memorizes answers might ace one specific test, but they'll completely fail when the questions change. A student who really learns the concepts can handle any new problem you throw at them. That's exactly what we want from our CNN. So how do we force it to learn? Well, we've got a couple of clever tricks. First is data augmentation. We take our training photos and just create tons of new versions. We flip them, we rotate them, we zoom in. This teaches the model that a cat is still a cat even if it's upside down. The second trick is called dropout. Imagine a basketball team where at every practice, one player is randomly told to sit out. It forces the others to learn how to score without always passing to the star player. That's dropout. It randomly turns off parts of the network, forcing the whole system to become more flexible and robust. Building one of these incredible models from the ground up can take weeks, even months, and it requires a mind-boggling amount of data. But thankfully, there's a brilliant shortcut that almost everyone uses. And it's for a very good reason. I mean, it's just not practical for most people or companies to start from absolute zero. The amount of data and pure computing power you'd need is just staggering. This amazing shortcut is called transfer learning. The idea is so smart and simple. You take a super powerful model that experts at, say, Google or Facebook have already trained on millions of images. That model already knows how to see basic things: edges, textures, shapes. You just take that knowledge and tweak it a little for your own specific job. You're literally standing on the shoulders of giants. And the playbook is pretty straightforward. First, you pick a great pre-trained model. Then, you basically snip off its final decision-making layers and attach your own new ones, customized for what you need, like identifying different kinds of birds. Next, and this is key, you freeze all those original layers so they don't forget everything they already know about vision. And finally, you train only your new little layers on your bird pictures. It's so much faster and more efficient. Okay, so we've gone from pixels to matrices, we've toured the feature factory, and we've even picked up some pro-level shortcuts. Let's bring this all home. I mean, why go through all this trouble just to teach a machine how to see? Well, because the things we can do with this are completely changing our world. And this is not science fiction. This is happening right now. CNNs are the engine that lets a self-driving car see a cyclist, that helps a doctor spot a tumor on an MRI scan way earlier, and that powers the security camera that can tell the difference between a person and a stray cat. So in just the last few minutes, we've gone on this incredible journey from a meaningless grid of numbers to a system that can have a sophisticated, real-world understanding of what it's looking at. This is a monumental leap, giving machines a sense that for all of history was purely biological: sight. And that really leaves us with one last big thought. The question isn't if machines can see anymore. The question is, now that they can, what are they going to understand? And what new discoveries and challenges will come from that? Thanks so much for joining me for this explainer.